Hello, welcome to week 2, lecture 2. We're going to be talking about Newton's third law, weight, and mass. This is from chapter 3, 3-6, and 3-7. First, we will do an example of Newton's second law. Then we will jump into Newton's third law, and finally, weight and mass. So this example of Newton's second law, the question reads, a crate whose mass is 360 kilograms rests on the bed of a truck that is moving at a speed of 105 kilometers per hour. The driver applies the brakes and slows to a speed of 62 kilometers per hour in 17 seconds. What force, assumed constant, acts on the crate during this time? Assume that the crate does not slide on the truck bed. 1 second. We will work on this. Okay. So the first thing we should do is just write down our knowns, and then we're going to draw a picture. Well, knowns and unknowns. Okay, so we know the mass of the crate, which is 350 kilograms. We know its initial speed is 105 kilometers per hour. And the final speed is 62 kilometers per hour. And the time interval between those speeds is 17 seconds. Then unknowns. Technically, we don't know the position, initial or final, although we could set the initial. But we probably don't need those. Then we don't know the acceleration and we don't know the force. And the force is what we're asked for. Okay, let's draw a really beautiful picture of this truck. Oops. With the block inside. Like I said, really beautiful. Velocity that direction. Now we're going to draw our free body diagram, or really partial free body diagram, because I said this in the last lecture, but when we're just working in one dimension, we're technically ignoring some forces. They're not going to impact our problem, but we will take them into account in the future. So this is the positive y, this is the positive x. I'm still going to put the y coordinate axes on these. Just again, I don't want you to get too used to ignoring them because we'll bring them back. Okay, dot representing the box, and then the force acting on the box, which is, or I guess it's called a crate. Force of crate, force on crate from truck. Okay, so we have a drawing, our free body diagram, our knowns and unknowns. The next step is to use the Newton's second law equation and get what I call the system of equations, although for one dimension it's just a single equation, of the force. So sum of forces in the x direction is mass times acceleration. And okay, so this part is where we put like the forces. So if there was more than one force acting in the x direction, we would sum them up. But we only have one force acting in the x direction. But the other thing to know is that that force is negative. It's acting in the negative x direction. So we need to put our negative sign in front. So that's where our negative sign comes in. And because over here on our free body diagram, and also just like on our object, the force acts in the negative x direction. Okay. Now, in order to find this force, which is what we're asked for, looks like we need to find the acceleration because we know the mass, but we don't know the acceleration, but we know the change in velocity and time interval. So we can use those in our kinematics equations to find the acceleration. So let's look at our kinematics equations. First one, v final equals v initial plus a delta t. Then x final equals x initial plus initial velocity delta t plus 1/2 acceleration delta t squared, and finally v final squared equals v initial squared plus 2a delta x. So let's look at these. Okay, we know v final, v initial, and t, we want the acceleration, so that's good. We don't know x final. Technically, we can say x initial is 0. We know this, we know that, we know that. So that's two unknowns. This one, we know this, we know this. We don't know either of these, and time's not even in there, so it's like wasting one of the things we know. So obviously, this is the one that only has one thing we don't know, and nothing we aren't concerned about in this problem. So that's the one we're going to use. We're going to use this equation, v final equals v initial plus a delta t. But first, we're going to convert because our velocities are in kilometers per hour and our time is in seconds. We need to get these in more agreeable units. So conversion. Starting with the initial velocity, which is 105 kilometers per hour. Just gonna walk through this because once you get the hang of this, it's way easier, but initially it can be tricky to get the hang of doing all these conversions. So I'm gonna talk through it. You can skip it if you're an expert. So there's 1,000 meters in 1 kilometer. You can see how kilometers on top in my value and on the bottom in my conversion factor. That will cancel kilometers out, leaving me with meters per hour. Then I want to go from hours to seconds, but first we'll do minutes. 1 hour is 60 minutes. That cancels out the unit of hours. That leaves us with seconds. I mean minutes, excuse me. Next is seconds. 1 minute is 60 seconds. And then we can cancel out the minute. And this gives us an initial velocity of 29.2 meters per second. And then we do the same thing with the final velocity, which is 62 kilometers per hour times 1,000 meters per 1 kilometer times 1 hour is 60 minutes times 1 minute is 60 seconds. And this gives us v final equals 17.2 meters per second. Okay, now we can go back to our kinematics equation. I'm just going to pull it down here where there's room. Let's see, v final equals v initial plus a delta t, and we want a. So we're going to subtract the initial from both sides, and then we're going to divide the time interval on both sides. And that will give us acceleration equals v final minus v initial divided by the time interval. And v final is 17.2 meters per second. The initial is 29.2 meters per second. And the time interval is 17 seconds. So this gives us an acceleration of negative 0.71 meters per second squared. And that makes sense because it's braking, and so the velocity is going to the right, and when something is slowing down, that means the acceleration needs to go in the opposite direction. And so velocity is positive, acceleration needs to be negative to slow it down. I'm going to try and fit the last part here at the bottom. Let's see. So we had the force on the crate from the truck, negative, remember, because it's pointing in the negative x direction, equals the mass times the acceleration. And we want to know what the force is. So we can plug in what we know. We know that the mass is 360 kilograms. We know that we just found the acceleration is negative 0.71 meters per second squared. Those negative signs conveniently cancel out because the force and acceleration are in the same direction. And we get the magnitude of the force is 256 newtons. And if we want to think about the vector of the force is 256 newtons in the negative I hat direction. That's one way to write it. There's lots of different ways to represent that. Okay, so that was our example. I guess actually I'll go back over it really quickly, just what we did, and then we'll move on to the rest of the lecture. So we looked at our knowns and unknowns just from the problem itself. Then we drew lovely pictures and our free body diagram. There's only one force acting, so it's a really easy free body diagram. And then we did our sum of forces equation, where mass times acceleration equals the only force acting, which is negative. So actually, I want to pause and emphasize this. So the coordinate axes we drew, to the right is positive x, to the left is negative x. So that means when we do our sum of forces equation, we bring the sign in there. So mass times acceleration, just ma, but then the sum of forces, okay, we have our force, but it's in the negative x direction, so we have to put that negative sign in front. Then we also looked at this, and the problem asks for the force, but we don't have the acceleration, so we have to find that. So then we looked at our kinematics equations for how we should find the acceleration, and we saw that this first equation had only one thing we didn't know, which was acceleration. So before we used that equation, though, we had to do our conversions because they gave us our velocity in ugly units. And well, they're not that ugly, I guess. It's not like it's miles or something. Anyway, so we did those conversions. And remember, you just structure your conversions so that you cancel out the units you don't want. Then we went back to our kinematics equation where we did some algebra to get an equation for acceleration. So V final minus V initial is delta T, and that gave us an acceleration of negative 0.71 meters per second squared. And then finally, we can plug that back into our force equation to find the force, which is 256 newtons in the negative x direction or negative I hat direction. Okay, back to the slides. Now, Newton's third law says when one body exerts a force on another, the second exerts a force on the first. And these two forces are always equal in magnitude and opposite in direction. Let's look at this. We have an example of two particles, because physicists love to make things particles. Remember the spherical cow. So A and B each exerts a force on the other. And these forces are equal in magnitude. The arrows are the same size, but opposite in direction. These are also known as action-reaction pairs or third law pairs. It doesn't actually matter which one is the action and which one is the reaction. You can assign it to either one. Usually people will assign the action to the object of interest. So if we were trying to solve something with particle A, we would call this the action force and that the reaction force, but it doesn't actually matter. Some examples of action-reaction pairs. So let's say we have a book sitting on a table. The force on the book from the table and the force on the table from the book. I feel like I might have said that wrong at first. Let's restate that. Book sitting on a table. The force on the book from the table, and then the force on the table from the book. Okay, then we have the moon orbiting the Earth, and the action of the action-reaction pair might be the force on the moon from the Earth, and then the reaction would be the force on the Earth from the moon. Finally, a baseball being hit by a bat. We have the force on the baseball from the bat, and then the force on the bat from the baseball. Here's another example of a satellite orbiting the Earth. The Earth exerts a force on the satellite. That's what this is. And then the satellite exerts an equal and opposite force on the Earth. Let's look in a bit more detail at a book on a table. Okay. So the Earth pulls down on the book. So book, we're in this snapshot. In B, we're ignoring the table. And in C, we're ignoring the Earth. So, but this is the reality. Okay. So the Earth pulls down on the book with a force FBE, or on book from Earth. But the book does not accelerate because the effect of this force is balanced out by an equal and opposite force, FBT, or book on book from table, which is exerted on the book from the table, like I just said. And even though the two forces, FBT and FBE, are equal and opposite, they are not action-reaction pairs. And you might ask, why not? You said they're equal and opposite. It's because they act on the same object. So that's the other thing about action-reaction pairs. The forces themselves act on different objects. So you don't have action-reaction pairs on the same object. So the two forces, this force and this force, sum to zero, which is why the book isn't accelerating. And each force has a reaction force somewhere, but again, it has to act on a different object. So the reaction force of the force on the book from the Earth is a force on the Earth from the book, and the force of on the book from the table has a reaction force on the table from the book. And just, again, they act on different objects in order to be an action-reaction pair. Now we have a worker pushing two crates in a row, and we can examine the action-reaction pairs of forces in this situation. First, the worker pushes crate 1. So F1W, or the force on the crate from the worker, and the crate pushes back on the worker with an equal and opposite force, FW1, which is the force on the worker from the crate. Then crate 1 over here pushes on crate 2 with force 2-1, or force on crate 2 from crate 1. And we have an equal and opposite force, F12, the force on crate 2 from crate 1. And finally, the worker also exerts a force on the ground. That is how the worker causes the motion. And that is FWG is the force on the worker from the ground. And then FGW is the work that the ground pushes back on the worker. I'm sorry, I think I mixed those up, but it's there. Okay, now slightly different situation, still same concepts. We assume the Earth's surface is an inertial reference frame, and the acceleration of our object is g, the free fall acceleration, or the acceleration due to gravity, here. And that also tells us that the sum of forces, which is mass times acceleration, because again, this is Newton's second law, is actually equal to mass times the acceleration due to gravity, since the acceleration equals the acceleration due to gravity. So we have that situation where there is that force from the Earth on the object, but then what if instead we hold the object? It's no longer accelerating, but the force from the Earth is still acting on it. So the force on the object from the Earth, but there's also a force on the object from the hand. And if it's us holding the object, we also feel a force on the object from the Earth. And what we feel is the weight force, so the weight of the object. And weight is just the downward force of Earth's gravity on an object. It's given as W equals mass times gravity, acceleration due to gravity. and it points down or toward the center of the earth. Usually that's going to be down for us, but some situations it might be different. And a note, weight and mass are not the same thing. Mass is an intrinsic property of an object. It's the amount of stuff it is made of. Weight is a force that depends on the local acceleration due to gravity and the mass. And depending on the planetary body you're on or where you are in the universe, the local acceleration due to gravity is different. So the weight will be different. So that's all for this lecture. In the next lecture, we are going to work through some example problems.